Hello, my name is Reynard Ko, and today I'll be presenting Lab 3 for Physics 2212. Here's an overview of what the presentation will be about. And so first, as an introduction, the main purpose of this lab is to measure the magnetic field of a small magnet. And in the end, we will compare experimental conclusions with predicted distances for both the on-axis and off-axis. And concepts that will be used include the equation to find a magnetic field of a dipole, Biot-Savart's law, and the distance dependence formula. And you can see these formulas on the right-hand side here. Next, we'll be going over the experiment. The system of our experiment is the small magnet, while the surroundings are pretty much everything else, which includes the ruler, phone, and magnometer. The procedure is as listed. First, we want to make sure that the magnometer is orthogonal to the magnetic field of the Earth. Then we want to triangulate the location of the magnetometer chip on the phone. Here I use Post-it notes instead of tape, but the basic idea is the same. After that, we want to measure the distance between the magnometer and our magnet for both the on and off axes. And this will help with our data collection, which is on the next slide. On the left-hand side, you can see the recorded distances and magnetic values from the magnometer app. And on the right-hand side, you can see a linearization of this data, which helps with the calculation just a little bit. And here are the calculations. In the end, I got a magnetic dipole moment of 4.4545 amps times meters squared. Here is the data analysis continued, specifically for the off-axis field. And next, for our computational model, on the tops, we can see a function that I created in order to calculate the magnetic field. On the bottom here is the instantiation of 6 vectors, 2 being on axis and 4 being the perpendicular axis. This is just to make sure that the visualization of said magnets is correct, or sorry, of said magnetic fields at this respective locations. And then next, I created another magnetic field vector at a 45-degree angle this time. And so when all is said and done, this is what the visualization looks like. On the on-axis magnetic fields are red, perpendicular axes vectors are purple, and then the blue one represents the 45-degree vector for the magnetic field. And then next we'll be going over some conclusions. So first, one pretty big assumption that we made is that bar magnets as a magnetic dipole. The reality is a little bit more complex than this. And in terms of potential error, I think the largest error or source of error could be that the other electronic objects may have skewed with magnometer data. And this could have been like mitigated if I had done the experiment outside, but it was a bit windy that day. For the first hypothetical question, if I had not oriented my experiment to compensate for the magnetic field, and Earth's magnetic field would have interfered with the bar magnet's magnetic field, and the results would have been skewed in one way or another. And then as for the second hypothetical, we had connected 2 identical magnets end to end, then the experiment would result in my opinion, or in my hypothesis, the magnetic field would double, and this is because the distance between the north and south pole of the dipole would double. And if you look at the equation of the magnetic field, if you double the distance between the dipole moment, then you would also just double the entire value as the whole. And so, yeah, the direction would stay the same, but and only the strength would change. Thank you for listening to my presentation, and you have a good day.